Good afternoon. Thank you, Chairperson, for the nice introduction. And I also thank the organizers for giving me this opportunity, for this kind invitation. So let me start with my perpetual slide. I always get a great pleasure in introducing my institute. It is the Indian Association for the Cultivation of Science. It is the oldest, some problem? Here. Hello? Yeah. All right. Am I audible? Yeah. So this is the oldest research institute in Asia, and there are luminaries associated with this institute. What I wanted to share today is we are celebrating our 150th year of ISES, and it gives me great pleasure to be a part of this institute. So today I'm going to talk about this Hall effect family. Hall effect is a very famous classical experiment we learn in our MSc courses, wherein the Hall resistivity, which is developed across as a trans voltage when you apply a current through a conductor, is linearly proportional to the magnetic field which is applied across. Now, if the material is a magnetic material, along with this linearity, you will observe a hysteresis pattern which is associated with the magnetization of that material. These things were discovered by Edwin Hall in 1879, 1881, but then for the longest time, this third member did not arrive. This is the topological Hall, and this was discovered around 2009 in works of Tokura and other people, where they observed that there could be another Hall effect, essentially coming from non-coplanar spin textures which can be existing in a magnetic material. Okay? And one classical traditional way of looking at this problem is, we know that the ordinary Hall effect is linear in magnetic field, and we know that the anomalous Hall effect is linear in magnetization. So if you consider that the total Hall resistivity that you have measured is a linear combination of ordinary Hall effect, anomalous Hall effect, and topological Hall effect, you can subtract these using the magnetization of the system and extract the topological Hall resistivity. However, you have to be very careful, because true representation of topological Hall resistivity can be obtained by direct imaging of these non-coplanar spin textures, because there is a lot of assumptions in these kind of technique, because you're assuming that the magnetization is directly proportional to this resistivity, which in many cases is not the case. So in our work, we will try to address some of these issues, and I will show you how we achieve topological Hall effect. So topological Hall effect arises mainly due to non-coplanar spin textures. What we mean by non-coplanar spin textures? Like when we apply a magnetic field, what happens? The moments align along the field direction. But if there are some moments which are in a three-dimensional space, not in a plane, then we call them as non-coplanar. And so if, for example, three moments are making an angle, that curvature made by that angle is called the Berry curvature. And these are some of the identifications of non-coplanar spins. And one way one can achieve, so this is one criteria that you need. Another criteria that you need is the inversion symmetry breaking of that material. So many materials are inherently symmetry broken, but one way we can break symmetry in typical centrosymmetric materials is by growing them in thin films. Because a thin film, if you look at this film, it has different phases on both sides. So at the bottom it is observing the substrate, but on top it is, for example, air. So its symmetry is already broken. Okay? So using thin film engineering or thin film growth, we can achieve such kind of non-coplanar spins and also topological Hall effect. One of the techniques that we specialize is in the growth of epitaxial thin films. What we mean by epitaxy is, if we use a substrate which is a single crystal, here I am showing you a cross-sectional TEM, you can see the cubic arrangement of the atoms. So the film that grows on this substrate actually wants to mimic the substrate. So it grows with its lattice parameter as close as possible to that of the substrate. But identically, there are two materials which do not have identical lattice parameters. So usually the film might have a slightly larger lattice parameter or slightly smaller. And depending on that, it gives rise to strain in these films. And this strain can affect its properties. So this work we started a couple of years back. We are still new in the field. But when we started, we took a very common material, which is permalloy. Permalloy is an industrially applicable traditional magnetic metal. It has got large magnetic permeability, but it is centrosymmetric. It is basically an FCC crystal. So you wouldn't expect any non-coplanar spin textures to develop in that material. But what our idea was, so okay, it's basically a cube. Now what if we take a cubic substrate and grow permalloy and create a strain in that material, then essentially we can break its centrosymmetry. And so what we did, we tried to grow permalloy films on top of single crystal magnesium oxide MgO substrates. Now MgO has a larger lattice parameter than permalloy. So permalloy, in order to grow, had to stretch itself along the film, and it gave rise to a tensile strain. But such kind of growth is not easy, so we usually monitor the growth using an in situ REID facility. REID is a reflection high intensity electron diffraction. So you can consider if an electron falls on your substrate, and after it basically reflects, it gets diffracted through the single crystal planes. And what you are seeing as just lines are actually the crystal lattice planes of your material. And you can see that these lines are following for the film and the substrate, which gives us an indication that it is a single crystal growth. And this is another, this map is a reciprocal X-ray diffraction reciprocal space map, which shows you a single peak for the film as well as single peaks for the substrate, and the close proximity of the peaks indicate that the films are single crystalline in nature. So once we were successful in growing them epitaxially, we measured their Hall effect. So this is the total Hall resistivity that was measured at room temperature. If we subtract the linear portion, which is contributed by ordinary Hall, we are left behind with this portion, which is the anomalous Hall. And if we subtract the magnetization, we observed that there is a certain nonlinear feature which could be the topological Hall resistivity. Okay? So why this is a little bit interesting is because we are observing this topological Hall resistivity at room temperature, and it works at very low fields, and you can always see that there is a switch in the resistivity. So one always talks about quantum switches and things like that using topological Hall resistivity. But this is not confirmatory. So in order to further confirm it, we studied the film textures using magnetic force microscopy under different magnetic fields. And here you are seeing red and blue contrasts. The red and blue contrasts are basically magnetic moments which are aligned in plane, in downward direction and upward direction along your film. So when you don't apply a magnetic field, the domains are all randomly distributed. But as you keep applying the film, the domains get aligned along the magnetic field, and you will see that the red color is slowly covering the whole image. But even at a 0.2 Tesla magnetic field, when the magnetization is already saturated, you still see that there are some of these island kind of magnetic moments which did not flip. And if you zoom into these magnetic moments, they have a boundary, this white region where the magnetic moment is not well defined, but they are actually moments pointing in an opposite direction to that of the entire film. And these could be indications of non-coplanar spin textures. In this case, we tried to see them as skyrmions. So skyrmion is one type of a magnetic coplanar spins. There are many types of topological non-coplanar spins. In this case, we thought these are skyrmions. So then after that, we used micromagnetic simulation to see if these are actually skyrmions. And in these simulations, what we calculated is the topological charge. So the topological charge is basically the spin chirality that you can calculate using these already predefined models. And this is a Mumax software that we used. We input our experimental data, and we varied the Dvorsky-Moria interaction, which is the main interaction which drives these things. And we got a good match with our topological Hall data. And we can also see that under these circumstances, there will be stable skyrmions generated in these systems. Well, anyways, with these things, we tried to convince the reviewer. The details of the work are published in this paper. But we were not exactly happy because the effects were very small. So then we started thinking, how can we enhance this effect? One idea that came to our mind coming from a magnetic background is, what if we introduce an exchange bias and grow a heterostructure of these materials? Now, permalloy oxide is actually a paramagnetic material at room temperature, but if you cool it, it goes through an antiferromagnetic transition. And permalloy is a typical ferromagnet. So if you can grow a heterostructure of permalloy oxide and permalloy, you are essentially making a ferromagnet, antiferromagnet, typical classical exchange bias structure. And this is what we went for. The trick was to identify a good substrate. We observed that alumina substrate, especially the C cut of alumina, it gives us a hexagonal base. So permalloy, which is actually a cube, but the 1-1 plane of permalloy, which is actually a triangle, can actually epitaxially grow on this C-cut alumina substrate. And this is what we did. So inside the sputtering, we first grew permalloy oxide, and then we grew permalloy. And these are typical X-ray theta to theta scans showing just the single orientation of the heterostructures, supported by the reciprocal space maps, where you can see that the substrate and the material are all lying on the same line, showing good epitaxial quality growth. Then we studied the properties. So this is the magnetic anisotropy showing you the in-plane and out-of-plane magnetization. So the heterostructure gave us a very good uniaxial magnetic anisotropy, with in-plane being the easy axis of magnetization. When we studied the magnetic temperature dependence of magnetization, we observe that at a certain temperature, around 150 Kelvin, there is a drop in the magnetization. And this is coming from the antiferromagnetic nature of permalloy oxide. So we measured exchange bias at different fields, and here I'm showing you a plot of the exchange bias field plotted along the perpendicular direction and parallel direction. Here perpendicular means out of plane of the film, like if this is your film, out of plane direction, and parallel is along the film plane. And we observed in the out of plane direction, below a certain temperature, there is a rise in the exchange bias field. And this is all coming from this permalloy oxide. Okay, all very good. What happens to now the topological Hall resistivity? So we measured the Hall and room temperature topological Hall resistivity. There was not much enhancement at room temperature, and that is understandable. Why? Because permalloy at room temperature is just paramagnetic, is not contributing much. But as you cool the system, when permalloy becomes antiferromagnet and the exchange bias field rises, we observed that there is a huge rise in the topological Hall resistivity. So this was another technique how one can enhance topological effects. But we were still not happy, because for a device, you don't want to operate it at 30 Kelvin or 10 Kelvin. The goal is to operate it at room temperature. So this brought us, these are the other checks. We did the magnetic force microscopy. Again, got evidence of very well-formed skyrmionic features. Micromagnetic simulations were also performed, which supported the magnetic force microscopy. So if you want to have the details of this paper, this is recently published in APL. Okay, moving further along. So we were not satisfied. So what we wanted to do is, why don't we make a structure of a magnetic metal along with a magnetic oxide? So we took one of our old studied material, which is LSMO, it's a lanthanum strontium manganite, which is a well studied half metallic ferromagnet, and on top of that we grew permalloy. Now the trick with LSMO is one can change its doping and change the carrier concentrations from N-type to P-type. So the way we grew our LSMO, we grew LSMO as a P-type material. And permalloy is a metal, so it's an N-type. So at the interface, we could create a P and N kind of a change in the carrier concentration. Okay. And in another structure, what we did is we had this LSMO and permalloy, but in between them, we grew a sandwich layer of a ferroelectric material, which is barium titanate. So what we are trying to do essentially is, we are trying to now manipulate the interface, and we are trying to create an electric field at the interface, which will be in the out of plane direction. And we want to see if this electric field can change the topological Hall resistivity of permalloy. And this idea is related to the idea of a Rashba spin orbit interaction, where interfacial electric fields can enhance the topological Hall resistivity. And of course, growing these structures is non-trivial, because as you keep growing different materials on top of each other, there are defects introduced in the interface. So a lot of time went in the optimization, but they have very good lattice, closed lattice parameters, and we used a combinatorial PLD for the oxide layers and sputtering for the metal layers. So this is the read patterns of the heterostructure. You can see good quality crystalline growth. And also in the XRD, you can see only one orientation of all the layers, confirming the high quality epitaxial growth. We have also done reciprocal space maps, similar to what I have shown earlier. And as you can see, as the number of layers increase, they don't really fall on a single line, because the strain between them kind of increases. But eventually they were all single crystalline. And we also calculated the in-plane and out-of-plane lattice parameters. And once you get the lattice parameters, you can also calculate the strain in these structures. Okay? Okay, this is a cross-sectional microscopic picture of this heterostructure. You can see the substrate, all these layers. And then you can see the MGO and LSMO interface, and the LSMO BTO interface, and then the BTO permalloy interface. And here you can see BTO is very well, highly crystalline, showing up almost cubic-like symmetry. But since permalloy is grown by sputtering, there is a lot of interfacial defects on that interface. So what happens to now the topological Hall resistivity? Again, we perform the same experiments. Here you can see LSMO gives you a positive slope, signifying that it has got a P-type carrier. All the rest of the materials have N-type carrier. And then when we extracted the topological Hall resistivity, we observe that it got highly magnified than the single layers. Okay? And these numbers are, according to literature, as giant topological Hall resistivity compared to the single layers. And what is more interesting is this is an observation at room temperature. But the details of the work on why this enhancement is happening were still not very clear to us. We, of course, performed the magnetic force microscopy. Again, we found out there are skyrmions developed. But then we collaborated with Professor Sayantika Bhawal, who did some of the theoretical support on these structures. Of course, one can understand, like, mapping these exactly into DFT is non-trivial. But what they were successful in doing, they did their modeling on a skyrmionic lattice. And then they varied the alpha parameter, which is the Rashba spin orbit coupling coefficient. And what they observe is, as they change the alpha parameter, the band structure becomes quantized, and this is an indication of a skyrmionic lattice. Although in our case, it is not exactly a skyrmionic lattice, our skyrmions were much larger, but this does show that one can change the Rashba parameter and change the topological Hall resistivity. So then we did how good is our material. So this is a figure of merit calculation where we have collected all the reported materials on topological Hall resistivity, but we restricted them to one parameter. We restricted this to a magnetic field of 1 Tesla. below 1 Tesla, because typically if you want to make a device, you don't want a magnetic field more than 1 Tesla. What we observe is some of the oxides have given very huge numbers, but most of these values are at low temperature. And considering that, we reported numbers which are around a room temperature but having considerably high values. So the details of the work are in this PRM paper. If you're interested, you can go through it. Okay, now remember we had already introduced the barium titanate at an interface, and that had a purpose. Why? Because barium titanate is a ferroelectric material, so it has a spontaneous polarization. So there is a built-in field which is already there. But it can also change its polarization with voltage. So what it allowed us to do is to apply an electric field or a voltage from outside and tune the anomalous Hall resistivity. Okay, so now you have an additional knob, because this polarization in barium titanate can be tuned by voltage or electric field, and we wanted to see if that changes the anomalous Hall resistivity. So this is again the growth of these materials, and this time again we grew it on two different kinds of single crystal substrates. One was the MgO substrate and another one is lanthanum aluminum oxide substrate. So you can see all these structures are growing in the 00100 orientation. The reciprocal space maps again show good high quality crystalline growth. So this is the interface of the heterostructure. So you can see that the lanthanum oxide and LSMO have a very sharp atomic interface. It's almost difficult to identify which phase is which, and there is almost, it grew with no defects within this image. And the SAD images also in the inset confirm their epitaxial growth. Okay, but as the number of layers grew, so for example in the barium titanate LSMO layer, we can start to see some dislocations, some defects. And of course in the permalloy layer the defects are much more. But overall the structure is highly epitaxially grown. Okay, we confirmed the ferroelectric polarization of BTO also using piezo force microscopy. Here in the phase image you can see the hysteresis loop of barium titanate, and when also we did poling and unpoling measurements, we can see that the polarization reversal is happening in barium titanate. This confirmed the ferroelectric nature of barium titanate. We also did polarization vector maps. What we do in this is, so these were done in collaboration with Pawan Nakula from ISC Bangalore. So they actually traced the displacement of the titanium ion in barium titanate, because it's the displacement of the titanium ion which gives the polarization. And what they observed is the polarization vectors in two different samples are 180 degrees out of phase. What I mean by that is, here you can see most of these red dots are around this 90 to 45, and here they are almost 180 degrees apart. And this is due to the different directions of this inherent spontaneous polarization in barium titanate. And so this is the experiment then we did. We measured the Hall under different applied voltages, and then here I am plotting the maximum Hall anomalous Hall resistivity as a function of the bias voltage. And what is very interesting to see is, as we change the bias voltage, there is almost a 93% change in the anomalous Hall resistivity. Again we went to theorist Shayantika for her help, because we didn't really understand what is the internal structure. And what they realized is, so what they're showing here is a barium titanate band structure when you introduce Rashba spin orbit coupling. Basically the band structure of barium titanate separates when you can introduce Rashba. And the Rashba parameter is actually related to the displacement of the titanium ion, which is related to the polarization of barium titanate. So they could relate Rashba spin orbit coupling with the polarization of barium titanate, and they show actually it changes sign. So this is the conclusion of my work. So I have shown through strain engineering one can achieve large topological Hall effects in permalloy thin films. One can introduce exchange bias, enhance this effect. One can design different interfaces of metals and oxides, and see this Rashba kind of spin orbit coupling. One can even introduce electric field control of the anomalous Hall effect. And all these are reporting data which is at room temperature and low fields and device applicable. So I would like to thank my group members. The work was mostly started with Nasir. He's doing a postdoc in Europe in Charles University. And then it was carried forward by Kusumpal. Kusumpal has a talk tomorrow on this metal oxide heterostructure. So if you have time, please attend. And then I would like to thank my collaborators and the funding from ANRF and Technical Research Center, ISES. Thank you for your attention.
So the session is now open for questions.
Yeah.
Just I was wondering, you have come across oxygen vacancy in all these samples, and what is the role of that? Because the properties should be highly dependent on.
So basically, we could not detect oxygen vacancies in most of these samples. Oxygen vacancy basically changes the conductivity of films because it's a charge center. So that is a separate study in itself. But typically in these kind of materials, see, oxygen vacancy is something which you cannot avoid. But its role is not that significant compared to the magnetic properties that we are studying.
In terms of transport, there is
it's not much different, yes.
Thank you for nice talk, sir. So here, 3 pieces of work you have shown about skirmions. So when you do the MFM, so how these skirmions are evolving with the, in the 3 types of structures, one was strain one, then this heterostructure ones. So how the skirmions are evolving, let's say in terms of density or size?
Actually, in all the structures, if you have noticed that we are actually measuring permalloy, right? So the skirmion density changes slightly due to the underlayers, but the size of the skirmions were roughly the same. Because those skirmions are actually coming from the DM interaction within permalloy. And now you are enhancing the skirmions by putting underlayers. So one case it's an exchange bias underlayer, one case it's an oxygen oxide underlayer. So you are changing the magnetization in that case, right? But the skirmions are typically coming from the bulk permalloy only. So they are not changing that much.
So in that scenario, how your topological Hall effect is like changing?
That is a very good question. Actually, we think that the size, what happened? So I will show you, like here the size became larger, like in some of these. But you have to understand, so this size is larger than the one that you observed in the single film. But see, when you are doing an MFM, you are still actually scanning a very small area, right? And when we are doing our measurements, we are actually measuring entire bulk of the material. So it's very difficult to correlate such localized changes into global effects. So what we believe, it's not just the skirmions that are coming into picture, it is the Rashba spin orbit coupling which is actually changing the anomalous Hall conductivity.
So that Rashba spin orbit coupling is also
an important part. We can always discuss. Yeah.
Thank you, sir, for a very nice talk. So my question is that by layer of LSM1 BTO, you've grown in 2 different samples. One is LAO and one is MGO, which will give you one is like compressive strain and one is tension.
Exactly, that was the idea.
And, therefore, you are getting, I guess, for that the Hall effect, the value is same, but the slope is not same. Like one is suddenly increasing,
yes.
One is.
Actually, that's a fantastic observation. I didn't. You catched a very. So let me go. So here I didn't mention, but here when we did this coercive field of barium titanate, so you see the coercive field in one case is very large, and in one case the coercive field is very small. And what we are saying, the spin orbit Rashba coupling is related to the polarization of BTO. right? So in one case, this change in the polarization of BTO should happen at low voltage, and in one case it should happen at large voltage. So this is exactly what you're seeing in this graph. So here it is happening at 0.6, 0.5, and here it's happening around 2. So it is related to the coercive field of this barium titanate layer. Because when you have a coercive field, the moments change direction, right? Does that answer your question?
Like how it is affecting the structure that this thing is happening. Like obviously strain is doing something to the BTO. Or
Strain will change its spontaneous polarization. But now we are applying a voltage. So BTO, there will be like the polarization will happen in BTO. But as you will change the voltage at one point, the direction of polarization will flip. And that's what is happening at large voltage, and one is happening at small voltage. You can talk to Kusumpal. He just submitted his PhD on this, so he knows much more than I do. So maybe he will be able to answer you better. Maybe we can continue after with the time. Yeah.
So there are definitely more questions, but you should clarify afterwards with the professor, and let us thank him for a wonderful talk.
Thank you. Thank you.